Hey there, and welcome to the stream. Let me just close these things down. Right. So, what we are looking at right now is just a live debug stream. I should probably go rename it on YouTube. Yeah, I'm gonna make this a window capture. I can't do that. That's probably why I haven't done it. I wonder how that's rendered. Anyways. Man, the new YouTube studio is annoying. Yes, I want to do things that aren't there. Oh, I have to click through an extra step. Okay, that should do it. Let me just share this with someone. Hey, welcome to the stream. I'm just sending out some links here. Watch me bug hunt and some CVP code. Then come hang out. Right. So let me bring up chat. That's there. No, not top chat. All chat. Okay. Right. So let's go over what I am trying to do. Right. What can you see? You can see that stuff. So, oh my god, this is a mess. I need more screens. Don't you always? Anyways, so this is the hardware. It's fairly simple. What you can't see in here in power handling is someone is telling me not to alt tab to pawn. I'll do what I damn well please. But yeah. Anyways, so what this is it's just a small access system for the hackerspace that I'm a member of. And it just takes an RFID card. It uses an ESP8266, and then it reads the RFID card, checks with the local server, and if they have access to the machine that this box is on, they will determine by which API key is loaded. They will be granted access, and it'll turn on power to whatever device they're using. So I am responsible for, well, it's not really something people get responsible for. It's just, hey, we need this, and then the idea floats around for long enough, and then someone interested picks it up. So yeah, I decided to work on this. Um, so yeah, all of this over here on the right is normal, except for this sense bit here. Actually, I got this for this exact reason. Here we go. So yeah, this bit here is new, and well, the entire bit over here is new. So normally they don't handle the power through the PCB, but that is something I'm doing here because I also need to do current sensing. So the way we do current sense is, let me see, I didn't plan this too well, because I do in fact need this now. The way we do current sense is through an ACS 723 current sense chip, and these are really neat. These have a Hall effect sensor inside, but basically they're just a short circuit between two pins. Let's see if they have a picture of the internal rendering from Allegro. There you go. Oops, there you go. So if we open the image in a new tab, that did not help. Anyways, what you can see here is there's just basically a short circuit right here that the current flows through and then out again. So they're very low resistance. And the particular one that I have is a 10 amp bidirectional, so it's plus minus 10 amps. And that's only really limited by the gain they have internally. You can get these up to 50 or 100 amps, I believe. And the only thing that changes is how many millivolts per amp you get. So yeah, Hexacube Hertz, there's a door giveaway. Why in the world do you need a door? What have you done? I thought you were putting up walls. Anyways. Right, so let's see what the table says. Yeah, you can get them up to plus minus 40 amps. Okay, but yeah, basically it's just determined by the gain here. So yeah, that's what I'm doing. This power monitor stuff. And this worked kind of on the original firmware that I worked on, and that is most of this code over here is well, all of this up here is libraries. This is some library stuff too. So the stuff I did was I added this current sense logic here, which just does some peak current, because it's AC, it just does some peak current measurements. And then if it hasn't been above a certain threshold for a certain amount of time, it returns not printing. Oh yeah, I should probably tell you why we do this. So if you have access to, this is for the 3D printers. So if you have access to the 3D printers, you put in your keycard, and you get, it turns on power for the 3D printer, and then you start a 3D print, but you need these keycards. These are the keycards we use to get into the hackerspace. So you can't leave it there in the machine. All the other machines, laser cutters, lathes, stuff like that, are things that you have to be at while using them. So they have just relied on you leaving your keycard in the reader. You can't do that with 3D printers. So you have to be able to determine if it's in the middle of a 3D print or not. So that's basically just measuring power consumption. Right. So with that, right. So that worked. This current reader class. We had a few issues with it that we didn't sort out, but it became obvious to another guy at the hackerspace that people would want to extend this access control system with different features. So in my case, I wanted to add a printer functionality to it that did current sense, which was special. And he wanted to make a camera control system, because we have surveillance cameras that runs out there when there's no one there. So he wanted to try and work on automating that. So he is a software student. So he, yeah, development student, program student, whatever. And he wanted to make it class-based. And I've had a single course in object-oriented programming, and I like the idea. So that's what we did. And that's when the problems came back. And these problems have proven very perplexing, and we're still working on them. So that's what I'm still working on. The problem is that the card reader just spits out the red data over serial, and we read these in through software serial. And this has been working flawlessly for, well, ever. So if we just take a look at this code here, so let me just define shit. I should highlight this down here. So now this code up here is inactive. So this sanity check here just includes the Arduino headers, includes software serial, sets up software serial, sets up normal serial, begin and software serial, writes out a little line, and then it just prints what it reads, and this gives us the correct data. This is actually the data you see here on the logic analyzer. So this is a dummy tag that I was out and picking up just for testing. And what it does is basically just it has this header here, so that's 2, the value of 2, and then it has 10 bits of data, and then 2 bits of CRC, and then a tail of 3. So yeah, that's how these tags are formatted. And for some reason, so when I run this code, that works fine. But for some reason, when I then do this and run this code up here, so let's go through that code. I set up a printer controller. Well, I have an object pointer here, so this is a pointer to the object of type printer controller. Then I assign that to a new printer controller, and then I just continuously call update this controller's update function. So if we look at that, that's printer controller. That would be there. So its update function just calls access controller update, and then it does some printer specific stuff, which is just current handling and current reading. It also does other, so this relay check is what we use to determine if the relay should be on or off. This is different between classes as well. So in the case of the printer, it's a state machine where it can either be idle, in progress, or cooling down, and then there's different checks associated with that. For example, in idle, it'll do access control checks, wait for new cards, and if there's a new card, turn on power and allow you to start a print. If it's in a print, it doesn't care about the card, it only cares about current consumption, and if it's cooling, it only cares about the time it's been cooling, and it'll allow you to put in a new card and start a new print without having to wait for it to cool down. And then there's a default state, which should never happen, and I can't see how it can, so what? Anyways, the problem is that our card reader class here, right, okay, so the update class, it also calls ACS upgrade, and ACS whatever update calls card reader update, updating the card reader to get the data. So that's this stuff here. I was doing some testing. I can't remember what testing that was, so I just set this to 0 permanently and then did something. But let's put that back because I can't remember what I was doing, so let's not do that anymore. So what we do here is we just read the bytes available on mserial, and right, that's another weird thing. When we're running this code down here, if we try to read serial when there's nothing available, it gives us -1 as an error. When I'm running this code up here and just constantly reading software serial, it gives us zeros back. Now that means that software serial read a 0 byte. For software serial to do that, so software serial is based on interrupts. This has been a few days of me just digging through code to get to this point, so if I'm being a bit fast, that's why. Anyways, the way this is set up is just you have, well, so 16 and 11 can apparently not be used for interrupts. So you have these, 6 plus 4, you have these 20, not really 20, no, I mean, no, 1, 2, 3, 4, 5. Yeah, we have these 10. Wow, I'm good at counting. It's the stream, I'm telling you. Yeah, we have these 10 interrupt capable pins. And there's, so they set up a function here. This iCache RAM attribute just tells the ESP compiler to keep it in RAM. Well, you need this for interrupt functions. Right. So it just sets up this function here. So software serial interrupt service retrieve 0. It associates that with, so the function here is basically call. So, okay, so if you're not familiar with C++ and objects and calling functions of pointers to an object, so if this is a pointer to an object, then you call members of this object, so functions that are in this class, you call those with an arrow, and it calls the rx read function on that object. So It's just set up like these 10 here for 10 different objects, and then these are lined up in this function here. Well, no, it's not a function. It's I don't know. It lists these so that you can pick the right one depending on which pin you're associated with. And then down here it just sets the so the pin here. So in our case we're using pin 14. So it just sets this object entry here to the pointer to the object of software serial that you started. So yeah, that's what you do. So what that means is that anytime there's a pin interrupt, and let's see, that's set up in begin. Where is begin? Well, anyways, no, I can find it. Here we go. Yep. So if you want to enable receive, if it's a valid receive pin, and if you actually want to enable it, so this is true, attach an interrupt to this pin, assign it this function. So in our case, that would be this function right here, which is this function up here, which means it'll just call rxread when there's an interrupt. And then it just checks if it's inverted logic or not. And the default for minvert is false. So that means this tertiary operator will put this in. So falling. So basically it means it triggers in falling edge. There will be an interrupt. So what that means is that on every falling edge of the signal, rxread should be called. And you can see that's an iCache RAM attribute as well because it's an interrupt handler. And what they do here is basically just some timing stuff, because this is serial, so it's an asynchronous protocol. So they just do some timing stuff to read at the right times so that they're synchronized with the stream. And that's pretty much what they do here. And then they just put those, whatever they read, they put that in the buffer and store the receive value in the buffer unless we have an overflow. Right, so then another important thing up here is how does serial available work? Serial.available just says, ignore the first line. Yeah, ignore the first line. Available is m in position minus out position. So I think that's the pointer to where it's currently putting data into the buffer and where you're currently reading data out of the buffer. So that's how many bytes are left ready to be read. So right, so that's how available works. So what we did so far was a lot of different things that just kept confirming that that was not the problem. And the last thing we did yesterday before going to bed was check how many bytes it thought was available. So serial available just rises up super quick to the buffer limit, which is default 64 bytes. So serial.available just super quickly becomes 63 and just sits there. So somehow this read thing down here gets triggered. And if you look at the serial protocol, let's see if I can make that a bit bigger. Yeah, transition. So if you look at the serial protocol here, the way this works is it's high when idle, and then it goes low for the start bit, and then this is bit 0, this is bit 1, this is bit 2, 3, 4, 5, 6, and 7, and 8. So it's least significant bit first as well. But what that means is that if the rxread function is continuously triggered, no, that's not what it means. I'm rambling. If this data line is continuously read as low, it will continuously read 0. So it'll continuously fill up its buffer with 0. So for some reason in our code, the software serial buffer is filled up with zeros. For some reason, this digital read right here, I don't know if you can see that. Yeah, you can. So this digital read right here always reads 0, which is very weird. Right. So that's where I am now. So now I just want to make sure that this thing actually triggers this subroutine here on each falling edge. So what I'm doing now, I'm just gonna go in here and I'm just gonna say digital write m. Let's see, m. No wait, let's just pin 2. High digital write to low. Right, so now I'm gonna try and upload this. So let's open a, not this one. Let's open a PowerShell and let's upload it. So also, if you look at the window that I actually have above you guys, but if you look at that, and then I will put the card back in. So no, actually, I won't put the card back in. Anyways, what we have up here is just this is the data input. This up here is the UART decoding of it. So you just get the 10 bytes of data, 2 bytes of COC, and a 3. And then this down here is just connected to, yeah, okay. Just got an upload error because it's not the right serial port. So this down underneath there is just a signal that a pin I have hooked up to D4 on the Wemos D1 Mini, which is pin 2. So that's why you just saw me set pin 2 high and low really quick. That should give us a pulse every time this goes low. It should give us a pulse a little bit afterwards. So let's see if that actually happens, and we'll see what happens, basically. Okay. Now, another weird thing that Platform.io does is that if you update the platform.io.ini, so the config file, and that's even if I just, as I just did, change the COM port, it has to recompile the entire project because it thinks you have different build flags for it. Okay, so now it should be uploading. Yep. Okay, so let's see if this actually happens. This is currently running. I just have it on normal trigger mode, which means that it will not redraw anything if it doesn't see the trigger. The trigger is falling edge on the serial line. And let's see what happens. So something bad happened because it is lighting up green. Well, no, okay. Why is the LED constantly on the Wemos? Right, so this is already interesting. Let's do a single pulse. Let's trigger when this goes high instead. Ignore. Okay, let's trigger on this low again so we have something to aim for. Okay, it's over here. Okay. That's even weirder. So this pulses quickly every time that subroutine is run. Also, for some reason, some weird reason, the LED is now constantly on the Wemos. Yeah, I did a similar thing in here. What happens if I just uncomment these? Does the LED actually turn off? Why is that on? How can that change possibly turn that LED on? Is that pin 2? No, it can't be. Then it would be off. We can. Oh, maybe off. Like maybe negative is actually its default on state. Here, let's see. That's not the case. What in the world? It's constantly low now, and the LED is on. So I think that's the LED pin. Let's just see. There's a constant LED built in, which is defined as 2. Yeah, that's the LED. Okay, that's expected then. Should have picked D3 then. Interesting. Let's just reverse the logic then, I guess. You know what? No, let me just get the soldering iron up and running again, and let's just put that on E3 instead. Should be fairly quick to do. So, right, so we're not seeing the peak every time it should be reading, which I would expect. Right, this is interesting. This is annoying. Let's see, is the soldering iron on? Oh, hot, it is. Just to make sure it's not some sort of weird interaction with something interacting with the built-in LED, I just switched it to. I hope my logic analyzer doesn't mind me soldering a wire it's measuring. I guess we'll find out. Okay, it seems to be fine with that. So sometimes the LED turns off. Anyways, let's just change this pin real quick. Oh yeah, the LED would still be on because I am setting it as an output. So let's find pin mode. There you go. Yeah, okay. That is apparently just pin 0. Interesting. So I don't really know on the ESP if these are as horribly slow as they are on the AVR, but I might try some of the other ones if they are. So let's upload that. And let's see what happens. This is why debugging is terribly entertaining. I don't know why I decided to stream this. I guess I held out the faintest hope that some C++ expert was going to drop by completely by accident and just tell me exactly why this is broken. Let's see how broken it is. It's definitely not generating the amount of interrupts that it should. Right, that is interesting. Also, why in the world is it triggering there? I get why it's triggering there, but why twice? That must be some probing issues. Let's assume it's triggering once. Hmm. Let's try and load the dummy code on, see what happens. Compare known working and known broken. Huh. Oh, right. Okay. So this is what it should look like. So there's definitely something going on with interrupts. That's messing us up. I was wondering why it didn't trigger in all falling edges. I've been wondering that for a while, and I figured it would just have to handle it if it was in or not. But the way it does that is that so once there's an interrupt on the ESP, a flag is set, and you have to clear that flag before any other interrupt will be called. So they do that here at the end, right here. They clear the interrupt flag, and yeah. So this is what it should look like. A nice interrupt at the start of each packet. We can just zoom out a bit and fit the whole thing on the screen. Right. So I'm gonna write the guy I'm working on this with. Also, there will be some stream downtime now because I will just update the issue we have on GitHub with what I found out. I modified the software serial library to send a quick pulse each time the ISR was run. I modified the software serial library to send a quick pulse each time the ISR was run. Allowing me to see it ran as expected. The first image here. First image is from the sanity check code. This runs as expected. The ISR is called on the first falling edge and then isn't called before. Called for the rest of that byte as interrupts are enabled. Second picture is from our code where interrupts are very rare and even happen when they shouldn't. interrupts are falling edge interrupts, so they shouldn't happen during serial. Happen when the serial line is idling high. And then we need to put in the pictures. So this would be snip. And then oh. Yeah, what the fuck that. So this would be the first picture, then we need to load the old code again. Even though this is a very simple thing we've found out, it is way more than we had the last few days of why this is happening. This does not feel like this feels like this is definitely a cause of the cause of the problem. It's not just some weird anomaly that doesn't have anything to do with it. This might not be the cause of the problem. This might be a byproduct of the same problem, but knowing that there's issues with interrupts is pretty major. I think. I mean, yeah. Let's do a single. That's not what I wanted to do. Snip. Let's do single capture, single capture, single capture, single capture, single capture, single capture, single. Come on. All right, let's just trigger on high. I want one like, yeah, like that. That's gonna be fine. Not what I wanna. God damn it. So that the one that I'm using there uploads to Imager and puts the link in your clipboard, which is nice for chats. But on GitHub, they actually support just pasting images directly. So yeah. Okay. I'm just gonna have to check my text, change my text a bit. Instead of the second picture, the two next. Okay. Right. So I'm just gonna stop the stream here. I think I have to start dinner, cooking it, well, preparing tomorrow's dinner, because I want to do some I want to do a big batch of pizza dough that'll last me for a week or something like that. So I'm gonna get started on that, and then I'll just send this out to the people who are working on it. See what happens. Thanks for watching, and